Consider a string of a length L fixed at both ends. Such strings are found in many musical instruments, including pianos, violins, guitars. When a guitar string is plucked, a wave is produced in the string. This wave is reflected and reflected from the ends of the string, making a standing wave. This wave, in its turn, produces a sound wave in the air with the frequency determined by the properties of the string. So let me draw how does it happen. When you wiggle in the center of this string, there would be two sinusoidal waves going towards the boundaries and eventually reach the boundaries. Once they reach the boundary, they will reflect, and the reflected waves will travel through each other, and that will create a standing wave. This is how the standing wave will look like, and because the speed of the reflected wave does not change, therefore the wavelength and the frequency of reflected sinusoidal wave are also unchanged. So these are conditions that will cause standing waves. So to connect mathematical analysis of standing wave with the physical reality, we need to impose boundary conditions. Boundary conditions. So it's a mathematical statement that we need to say if you have the wave represented with a function y, x, t, 2a sine kx cosine omega t. I derived that in another video. It's called standing waves. You are welcome to stop here and go watch that and come back. So, and then boundary conditions would be y at x equals 0 at any time should be 0, and y at x equals L at any moment of time should be equal to 0. So this is the require nodes at both ends. If we look back in the picture, here we will see this one is x equals 0. We have a node. And on the right side, we also have a node. And that's a x equals L. Okay, now let's apply these boundary conditions for our function. So we would have y at 0t equals 2a sine 0 cosine omega t. That's the first condition. And then the second condition would be y x equals L t equals 0. So this can happen only, maybe I should write that down, the whole thing. So 2a sine kl cosine omega t. This can happen, will be met when 2a sine kl equals 0. And this is true whenever sine kl equals 0. Which leads us to say that the kl should equal n times pi, where n equals 1, 2, 3, and so on. So remembering that k equals 2 pi over lambda, I'm going to write 2 pi over lambda L equals n pi, from which I can find the lambda where the pi will cancel out. Then for nth lambda would be equal to L over n, where n equals 1, 2, 3, 4, and so on. So we are not using n equals 0 because L cannot be 0. So obviously we have to, and also it is in the bottom. So a standing wave can exist only if its wavelength equals 2L over some numbers, integers. So from here, we can also talk about the frequencies, at which frequencies the standing waves can exist. So a standing wave can exist. To find the frequencies, we need to recall that lambda f equals v. So frequency n would be v over lambda n, which will give us v over 2L over n, or that equals v over 2L times n. So the lowest frequency can happen, we're going to call it F1, will happen at V over 2L, and that corresponds to lambda 1 equals 2L. So this is known as fundamental frequency. For n greater than 1, higher frequency waves are called harmonics. Let me just write it for you. So harmonics, and each frequency can be represented with the fundamental frequency n times f1. So this would be harmonics for us. This condition, or this situation in which only certain frequencies are allowed, is called quantization. Let me write it for you. Quantization, and this is the situation when only certain frequencies are allowed. So possible standing waves are called modes, or normal modes. Now, to visualize these normal modes, let's draw the first mode, the second mode, and the third, maybe the fourth one. So when n equals 1, we have the first mode, our lambda 1 equals 2L over 1, and the frequency equals V over 2L. And so it will look like this. Only one loop, two nodes at the ends. When n equals 2, we are supposed to have two loops, like the number of n is the number of antinodes actually. So L2 equals 2L over 2, which equals just the L, right? So, and frequency 2 second frequency equals 2 times V over 2L. And it will look like something like this. So normal mode 2. So which will create 2 antinodes. So remember, n is the number of antinodes. And remember that fundamental mode, n equals 1, is the fundamental mode, and lambda, the wavelength, is not equal to L. Lambda 1 equals 2L. So just remember that too. So let's just draw the mode 3. N equals 3. We are supposed to have 3 loops now. 1, 2. Okay, so 1 loop, 2 loops, and 3 loops. So this one would be L3 equals 2L over 3. Frequency would be 3V over 2L. And well, let's do the fourth one. I'm sure you already can do it yourself. Maybe you have to pause the video here and do it on your own. Okay, so I messed it up. Let's try it again. I hope I did it correct this time. 1, 2, 3, 4, 5. No, that's n equals 5. Okay, well, let's write n equals 5. Then you will write the fourth one on by yourself. So that would be L5, that equals 2L over 5, and F5 equals 5 times V over 2L. So frequencies of normal modes form a series of F1, 2F1, 3F1, 4F1, and so on. The fundamental frequency F1 can always be found as a difference of delta F. So if you take if you want to find the fundamental frequency, you take 2 frequencies and subtract from each other, n plus 1 minus f n minus 1. Okay, so and don't forget that these frequencies, when n is greater than 1, are called harmonic series. Those are actually the whole thing is called harmonic series. Well, I'm going to prepare more videos on examples, solving examples. Stay tuned, and thanks for watching.